Our next speaker is Professor Dirk Englund from MIT. Dirk.
Thank you, Stefan.
It's in PowerPoint. Hopefully it's working okay.
Oh, that might not work in PowerPoint.
Yeah, the internet's not working on this machine.
Okay. All right, this could be surprising.
I checked through it.
Okay. All right, so good morning, everybody. So thanks to the organizers for getting me a chance to participate in this fantastic meeting. So what I want to focus on here is the development of these photonic integrated circuits for applications in quantum information processing. And in particular, I want to focus on PICs for quantum repeaters and quantum networks. So the idea with the quantum network is that you'd like to have a layer on top of the internet today that allows you to distribute quantum states with high fidelity and high speed between users that might be across the continent. And if you could do that, then perhaps you could produce, let's say, an entangled state between Alice and Bob, maybe thousands of kilometers away from one another. And if they can make this entangled state, you can see here that if Alice makes a measurement on her qubit, then Bob will get the same measurement on his qubit. And this is true no matter what basis you measure in, as long as they're the same bases. And in this way, Alice and Bob, by just making measurements on these, what hopefully would be high-fidelity entangled states, could produce a series of correlated numbers that they can then use as a one-time pad. So once you have a one-time pad, you can use a telephone line to communicate securely. Just binary addition of that key that you've produced in the quantum way to your classical message. So that's the idea underlying quantum secure communication. There's a number of other things that this kind of a quantum internet could allow you to do, testing fundamental questions about quantum mechanics, perhaps networking quantum computers together, blind quantum computing. Philip Walter might have talked about some of this yesterday. Perhaps you can make better sensors, and there's probably many other applications that this kind of a quantum internet could run that we simply don't yet know. But the problem is that photons get lost in fiber. Over 100 kilometers, you only have a 1% chance that a photon getting in on one side will actually make it out the other end. So if you want to go long distance, you have to do something different. We can't use classical repeaters to amplify the signal, but there's a clever idea put forth by Hans Briegel already 20 years ago that shows a way around this. And the idea is, in essence, to entangle small quantum computers that are placed throughout the network, placed sufficiently close to one another, maybe tens of kilometers, so that photons can, in fact, bridge that distance. And what you can do is, by sending photons across that distance, herald, by measuring if a photon has made it to the other end, the transmission and entanglement of some memory. Perhaps that memory could be photons, perhaps it could be electron spins, whatever your memory is. You can herald the entanglement between nearest neighbor nodes, and I've indicated this here in red. And if you then break up the link between Alice and Bob into these smaller segments, you now have a chain of entangled memories. And then by doing just local qubit operations, 2 qubit gates or a Bell state measurement perhaps at every node, you can disentangle that node and leaving the nearest neighbors entangled. And in this way, ultimately produce that entangled state, that Bell state that Alice and Bob wanted in the last slide. Okay, so what do you need for this kind of a repeater? The requirements are that at least you have 2 qubits, one of which you can entangle to the person on the left and the other to the person on the right if I'm the repeater. And then once I've done this, and I know that I've done it by heralding on photons, then I need to be able to produce a relatively efficient 2 qubit gate between these qubits. And that's the requirement. So you want to have 2 qubits with a reasonably good way of making a Bell state measurement, ideally a 2 qubit gate between them. All right, so this is now what I want to talk about in the remainder of the talk is our efforts in building these kinds of quantum repeater nodes, where in particular we are using photonic integrated circuits to connect multiple quantum memories. We would like to do this not with just 2, maybe with 10 or 100 or so, which gives you the ability to multiplex, so you can run things much faster than if you just had 2. But to make this thing work, you need a lot of things to come together, and so I'm going to talk about these photonic integrated circuits that we are outfitting with artificial atoms. In the case of our work, color centers and diamond as our quantum memories, and our spin-photon interfaces, and also a bunch of other technology that has to come together, for example, photon resolving detectors. And then look at two particular applications. One, the one that I just mentioned in quantum networking, and then at the very end, in the last minute or so, I want to talk about some ideas in using these quantum repeaters as a modular quantum computer. All right, so this was work done definitely not in isolation. We had, so here's the team of PhD students and postdocs at MIT, but we've had tremendous collaborators helping and continue to work with us on these efforts. All right, so let's take a look at one particular color center that can be used as a quantum repeater node. This is the most deeply studied in diamond, the nitrogen vacancy center. It consists of a nitrogen substituting for a carbon in the diamond lattice adjacent to a vacancy in the lattice. If you dope this thing so that the nitrogen vacancy center is in a negatively charged state, then you get in the ground state a spin triplet, an electron spin triplet. And so now a spin triplet corresponds to two electrons along the quantization axis, up, against it, and anti-parallel. Spin up, spin down, plus spin down, spin up. Right. If you put two electron spins, their dipole moment gives you an energy penalty that, based on the electronic structure of the NV, comes out to something like 3 gigahertz. So indeed, if you look at the ground state, the ms equals 0 magnetic step level, where the electron spins are anti-parallel, like you would want two bar magnets, you want them to be opposite like this, that ground state is 3 gigahertz or so apart from the +1, -1 magnetic sublevels. So you have 3 levels, a qubit you want 2, so you can apply magnetic field to Siemens split out one of the levels, and then you can use 2 that are energetically resolved. Okay, so that's the ground state qubit. You gotta ask, okay, how good of a qubit is it? How long can you maintain coherence? How long can you maintain a phase between these two states? And the answer is, it's quite good in diamond, in large part because it's magnetically very quiet material. Diamond is made mostly from carbon-12 nuclei, which have no magnetic moment. And so the spin coherence can be maintained for about a second or so at low temperature for the electron spin. In addition, remember that the repeater requirement was that we wanted at least 2 qubits with a reasonably efficient gate between them. So fortunately, in the case of the NV, there are ancilla qubits, namely the nuclear spin of the nitrogen. That can be either nitrogen 15, which is spin 1/2, or nitrogen 14, which is spin 1. That's an extra qubit. And you can use occasional carbon-13 nuclei, which are spin 1/2, as ancilla qubits. And these are magnetically coupled to the electron spin. Right? So you have actually a small quantum register consisting of a handful of qubits or so connected to light via the electronic transitions of the NV center. Okay. And people have, in fact, shown 2-qubit gates and even error correction and so on using this resource of additional nuclear spins. But now you want to couple this to a photon, and what you can make use of is spin-selective optical transitions. So in particular, if you illuminate the NV with a red laser field that goes ground state of the ms equal 1 to excited state of ms equal 1 magnetic step level, so you're addressing that spin configuration, then you can make it so, then that atom will scatter a photon, okay? But it will fluoresce. But if the electron state is in this configuration, spin up plus spin down, ms equals 0, then the incident light is detuned from optical transitions, allowed transitions, and it will not scatter a photon. So in one case, if the spin is in the right way, the atom will fluoresce. If it's in the other way, the atom will not fluoresce. So you have a spin-selective fluorescence, and that allows you to entangle the state of the spin with the state of the photon, where the photon, in this case, is a qubit encoded in the number state. There's a photon there, or there's not there in one optical mode. All right, so here, and that was already demonstrated some time ago by, for example, the Lukin group, the spin-photon entanglement. Now, if you repeat this twice, and then perform, so in A and B here, for example, and then perform a Bell state measurement on the photons that are in turn entangled with their electron spins, then you can project into, probabilistically working half the time, because the Bell state measurement only works half the time, then you can project into an entangled state of the electron spins. Okay, So this has actually been demonstrated already, and the leading group in this effort is the group of Ronald Hansen at Delft University, where they nowadays, actually it's very amazing, I think, they are able to generate the entanglement between electron spins in distant NV centers faster than the coherence decays. So this was a big milestone. If you want to build a house of cards, you need to put the cards together faster than everything falls apart. And that threshold was just breached last year. And they can generate entanglement at 35 hertz, whereas I already mentioned the decoherence rate is about 1 hertz. So you can go faster than it falls apart. That's great. That's a really important step in making these networks possible. But there's a long ways to go. 35 hertz isn't particularly fast. We could go way faster. And let me show you a couple of ways one can do it. Here's the low temperature spectrum of the NV center. It shows the zero phonon line. This is the coherent optical transition. But in fact, 97% of the emission goes into this phonon sideband. That is an incoherent emission. It couples to short-lived phonons in the diamond lattice and not useful for this quantum network, for quantum entanglement generation. So, cavity QD people say, hey, this is an easy problem. All you got to do is put your atom in a cavity, and by, thanks to the Purcell effect, it will enhance the emission that the atom is coupled to in that cavity transition. And in fact, we and a couple other people did exactly that. We put the NV center into cavities. Here, this is a cavity made of single crystal diamond, fabricated in a really difficult and tedious way. And sure enough, the NV center goes from this to this, where here 60% or so, rather than 2 or 3% of the emission goes into the zero phonon line. All right, so this, you look at the date here, this is already way old, this is from 2015. What have we been doing? Why don't quantum networks today use these systems? And the problem is that although we can modify the branching ratio tremendously, there's a penalty that we currently pay, which is the spectral stability, and I want to tell you a little bit about that. But before I do, let me just show you the advances that we have made in the fabrication of these diamond cavities. 5 years ago or so, we would make cavities by buying a piece of diamond, 200 microns thick for a few thousand bucks, a few millimeters on either side, and we would thin it down, all the way down to about 200 nanometers, which is half of a wavelength in diamond at 637 nanometers. So this is a really costly research endeavor when you buy expensive diamond and then you evaporate 99.99% of it. So De Beers, which is the parent company of the company that we buy this from, this is a fantastic idea. We should totally keep doing it. But we thought we need a more efficient way to produce these diamond cavities. And so over the years, the community has developed new methods of fabricating diamond. Here's a technique originally introduced by the group of Marco Lonker that works very well, where they keep the diamond intact, they just etch cavities on the top of it by directional etching. We also did some similar work on this. Nowadays, what we do is a different process that first etches cavities down into the diamond and then uses an isotropic reactive ion etching step to undercut the diamond. Okay, this took a while to develop. There's a couple of tricky ways to do it because it seems pretty simple when I say it, but it took a while to do. But the point is that we can now make rectangular cross-section 1D photonic crystal cavities like this one. And more recently, also, we were able to make two-dimensional photonic crystals out of just a bulk bulk crystal using this undercutting method. And I think cool thing about this is that this method that we now, after 5 years or so, have is really quite repeatable. We can make thousands of cavities on one chip. It works. The Q factors are better than what we can measure with a spectrometer. They're better than, I think, 20,000 is the latest number my student told me. And the optical properties of emitters are getting better, but they're not quite there yet. So here's some images. This is what these cavity arrays look like and so on that we can fabricate. But the catch is this. The catch is that if I look at an NV center, which deep in the diamond has a line width of about 12 or 15 megahertz, which is 1 over the lifetime of that emitter, when I put it in the cavity, the transitions are on the order of gigahertz. So here's a histogram of a couple of devices we measured, and you can see that many of the devices have NVs with line widths that are on the order of a few gigahertz. A few gigahertz versus 10 or 50 or 20 or so megahertz, that's 100 times or so worse line width than you would naturally have. We can combat that with some Purcell effect to some extent, but still, it's going to be, these photons are not indistinguishable, which means that in the entanglement generation, you would know where, since the photons come in at different colors, you would know where they came from. That would not produce the entangled state. All right, so we need more stable emitters. We are still hopeful that we can figure out this problem, which I would love to discuss with anybody who's interested, on making NV centers in cavity stable. It has to do with the surface preparation probably of the diamond and perhaps some material science that we don't yet understand. It's a very interesting problem, I think, on a material science side. And we are making progress. Every year our alignments get narrower. But we're not there yet. We're still a factor of 10 or 50 or so away from where we need to be. But fortunately, there are other centers in diamond that actually are spectrally very stable, the group 4 vacancy centers. And here's the silicon vacancy center, and you can see the silicon sits right in the middle of 2 vacancies in the diamond lattice, which gives it an inversion symmetry that makes it protected to first order to electric fields. It has no built-in dipole moment like the NV center does, so the energy transitions are more immune, more insensitive to stray electric fields, which we think is the primary cause for the spectral diffusion of the NV center. And so, and moreover, with silicon, we can go to our friends at Sandia National Laboratory, and they have a focused ion beam that allows them to implant silicon atoms directly into diamond structures, okay? So with very high resolution. So it's very cool. So you have this very stable emitter that you can just put where you want it with the focused ion beam. Here's a plot of showing how precisely we can do this. The answer is about 30 or so nanometers placement accuracy, which is good enough. Here's the ensemble line width, about 51 gigahertz. That's reasonably narrow for solid-state emitters. But let's look at a single optical transition of one of these silicon vacancy centers. It's about 120 megahertz, where the lifetime is about 3 nanoseconds. So this puts it close to the Fourier transform limit. So this is now actually a very stable optical emitter, which is what we wanted. Again, there's a catch. Okay, nothing comes for free. The spin coherence of the silicon vacancy center at 4 Kelvin is quite a lot shorter than it is for the NV. It's only, at 4 Kelvin, it's about 10 nanoseconds, whereas for the NV, remember, we had 1 second. But the Lucan group has shown that if you go to lower temperatures, dilution refrigerated temperatures, 100 millikelvin or so, you can recover a lot of that, and you can actually get about 10 milliseconds of spin coherence already. This is not necessarily optimized and so on. So there's a way to get around it, but we don't want to work necessarily at dilution refrigerator temperatures, kind of painful and expensive. Are there other emitters that actually combine the best properties of the NV, long spin coherence time, and the silicon vacancy, narrow optical transitions? And it's not yet proven, but there's good reason to believe that there are. The germanium and the silicon vacancy, tin vacancy centers in particular, look like good candidates. Recently, we showed that even at 4 Kelvin, we can get a greater than 50 microsecond T1 time, whereas for the silicon vacancy at the same temperature, it would be 10 nanoseconds. So it's a factor of 1,000 times or so better. We haven't yet measured T2 time. Here's the reference for that paper. We haven't yet measured T2 times. We're working on it. But we're hopeful that, in the not-so-distant future, we can have something that combines the best properties of narrow optical transitions and stable ground state. All right, moving on. If you want to do error correction, ultimately you will have to do some form of quantum error correction in your network nodes. You would like to use not one color center coupled to a few nuclear spins, but many. I want to have a node that has perhaps tens or hundreds of qubits with reasonably good coupling. So one way you could make that kind of a system is to produce clusters of diamond color centers that are sufficiently close that the electron spins couple. And the coupling for 2 electron spins at 10 nanometer difference is about a 10 kilohertz or so. So that's sufficiently good for us. So we've been working on making these kinds of clusters, and without going into detail, makes it possible to use the inhomogeneous distribution of emission spectra to actually super resolve individual color centers. And we can do that down to a few nanometers, as is shown in this paper. So that's the first step, that we can make clusters. We can look at every single atom in the cluster because they have different colors slightly. And moreover, we've shown that we can do single qubit readout with reasonably low perturbation on nearest neighbor qubits. All right. Moreover, you'd like to put these clusters we'd want to put these into chips so that we have access not to one such quantum memory, but an array of them. And that's the last bit I want to talk about here on the architecture. So the vision is sort of to make these color center cavity systems in arrays. Here's 8 of them, for example. And then I want to be able to switch any of these 8 quantum memories out into the quantum network. So you need some sort of an optical switch. Also, perhaps I'd like to be able to entangle any pair of these 8 qubits together. That would require me to send their light into a beam splitter photodetector, right, for the Bell state measurement. So what we want to make is basically arrays of cavity-coupled spin qubits coupled to this switch array. And I wanted to show you sort of the progress in doing that. So the big challenge for us is that we need to find a material platform that is transparent at short wavelength, that has low autofluorescence, that ideally has electro-optic properties, and a bunch of other requirements that make it suitable for coupling to these color centers that emit in the visible part of the spectrum. And so what we have been developing together with Rome Laboratory, with Air Force Research Lab, and Mike Fanto talked about this yesterday already, and with Raytheon BBN, is a photonic integrated circuit platform based on sapphire topped with aluminum nitride. Okay, and so here's just sort of like, the sketch of the devices we're developing: Bragg filters, ring filters. We can pick and place individual diamond waveguides that contain well-behaved color centers onto that platform. We can now do this with tens of them at once, so that actually makes it much more scalable. We can have superconducting detectors on this platform. This is done in this case under the leadership of Carl Berggren. And recently we've been able to show that we can individually address qubits using CMOS microwave circuits. I want to talk a little bit about that. Here's the circuit that we developed for the for the infrared part of the spectrum, just to show what the kind of circuit is that we would like to create. This was done with a foundry, in this case with OPSIS, and now lots of people are doing this around the world with other methods. We would love to have a foundry that works in a wavelength range in the visible part of the spectrum, but at the moment there isn't one yet that satisfies all of our requirements. But I'm hopeful that commercial interest will spur that development. In fact, a surprising offshoot from our work on these silicon PICs has been that they actually turn out to be quite useful for matrix vector products that are important in deep neural network computing in deep neural networks. And so actually, some of my students, Nick Harris, for example, who worked in developing these photonic integrated circuits with me in my lab, started a company that now tries to, that is scaling up really tremendously, the size of these PICs, with the hope of addressing the huge market of deep neural network accelerators, okay? So competing against NVIDIA and Intel and so forth. So I'm very hopeful that that process will play out, and as a result, what my return is, as the former PI of Nick, is that he will make these fantastic PICs that I can use and then apply to what we want to work on. And so, in particular, the platform would look like something like this. We have our quantum memories, we have our PICs, and we want to be able to address individual qubits, which requires you to apply microwave fields to individual qubits for the spin control. So we really have all of these parts now in place. I talked about this already. I talked about this. Very quickly tell you about using CMOS control, custom-designed CMOS control to control spin qubits. So the idea is like this. You have a diamond containing one or multiple NV centers or other color centers. Now you want to apply a magnetic field that allows you to turn the spin of that system. And what we've been doing is actually use TSMC foundry to produce these micro inductors directly using the metal layers of the CMOS. So these are tiny, have really sharp bends and so on, and that allows us to actually do electron spin resonance measurements on NV centers in diamond that are placed on top of this custom fabricated CMOS circuit. So it's not yet there, we can't yet control a single qubit, but I think we're reasonably close. But it does show that the method works. So by combining these technologies, we should be able to control the optics, control the spin, and do all the other parts that are necessary. So the hope here, last 2 slides, is that we will get to a point in the not so distant future where we can make thousands of well-behaved qubits, spin qubits, coupled to photons with a reasonably high yield process so that we can make this kind of a circuit that's illustrated here. You have an atomic memory, or atom-like memory in diamond, for example, connected to a switch, which can route light from that guy to Bell state measurements, beam splitter and photodetectors, together with to perform Bell state measurements with photons coming from other memories. So this would allow you then to entangle this quantum memory with that quantum memory. And in fact, by passing light through this switch, you could entangle any 2 pairs at will in this way and produce difficult, otherwise to realize, graph states. So that's the idea. And we wanted to see how powerful is this method? Is this at all, is this reasonable? Does this mesh with the numbers that we have? And so we considered, a simple lattice. Let's take a square lattice of NV qubits in this case. These are the dots here. And we say, okay, you repeatedly try to entangle a pair. When you do create a pair, then you draw a black line. That's those guys are now in an entangled state. We've applied a controlled phase gate. And what's plotted here as the red mesh, those are those qubits that are part of the biggest cluster state you've produced in this way. And there's an interesting thing from classical perturbation theory. This has been known for a long time, but when you use percolation theory on this array of spin qubits, you get a percolation threshold at 0.5. So if your probability of entangling nearest neighbor qubits is greater than 0.5, then you get basically very long-range cluster state where nearly all parts of the lattice are part of that cluster state. And that's what's shown here. If the probability is 0.6, then you see nearly all of the qubits are part of a cluster state, which means that you can connect any 2 qubits by just local measurements in a one-way quantum computing scheme. And the other thing is, how long does it take? And our estimates are that what this is showing here is the probability of succeeding in entangling nearest neighbor qubits. So if your probability of entangling nearest neighbor qubits is like, let's say something like 5%, okay, so you have a 5% chance of getting both photons into a photodetector, which is not unreasonable, then you would be able to generate this cluster after just a few hundred microseconds, which is much shorter than the coherence type of the NV, which is 1 second, right? So we're pretty hopeful that this kind of a system can, in fact, produce the entanglement fast enough so that we can use it for computation. We're not saying that the cluster state one-way quantum computing is necessarily the best possible way, but it's a reasonably good proxy to estimate the hardness of doing other types of quantum computing algorithms. And we also considered in this paper here that in principle these kinds of percolated clusters can implement quantum error correction at fault tolerance. So it's a tough thing to do, but in principle this thing would allow it for that. Right. To save time, let's go here to the summary. So over the last 5 years, there's been a tremendous progress, I think, in developing quantum repeater nodes based on photonic integrated circuits coupled to spin qubits in diamond. The cavities are working well. We can make thousands of them quite reliably. The quantum emitters are getting close to the properties that you would want, narrow optical lines and good spin coherence. Silicon vacancy is basically there if you are willing to pay a lot of money for the right temperature fridge. We're able to integrate CMOS electronics to do spin control. And the photonic networks it's still challenging, but I think there has been tremendous progress across the community in developing large-scale PICs, both in infrared and for us in particular in the visible part of the spectrum. So I think there's a very good there's a very good chance that in the next couple of years we'll be able to beat the repeaterless bound. We can do networks that do better than networks without quantum repeaters. And moreover, if you know how to control that technology well and you can make many copies, and that really is the benefit of solid-state systems, you can copy and paste perhaps 1,000,000 times or so, then you could think about making large-scale arrays of these qubits for modular quantum computers. So pretty excited about that. All right, thank you.
Time for a question. Right up here.
Hey, Dirk. So for the NV centers that you have that are interacting and it's also spectrally resolvable because they're close enough,
Yeah.
does that in theory allow you to do entangling gates and entanglement swapping with a higher than 50% probability if you do it without photon interference?
Yeah, exactly. Actually, that has already been demonstrated by the group of Dirk for 2 NV centers that were also something like 10 nanometers apart, but they were found by chance. They had a postdoc screening through many, many samples to find 2 NV centers that were sufficiently close. We hope that we can reliably reproduce such clusters, and then that coupling is deterministic. That's always on coupling. Well, you can, in fact, it's not always on. You can actually by putting the electron spin into the ms equals 0 magnetic sublevel, you can turn the coupling off. So your data qubits are in the nuclear spins. Imagine there's one NV center here, it's got a few data qubits. Another one is over here, it's got a few data qubits. You can move the qubit from the nuclear spin onto the electron spin twice, and then interact these 2 electron spins. Now you've done your gate. Go back into the nuclear spin and turn off the coupling of the electron spins. So that's how you would go about that.
Thank you, Dirk, again.
All right.